Hi, I'm Kurt Keutzer, professor of ECS at UC Berkeley, and today I'm going to talk about structural patterns in parallelism. So to put this in context, we've been teaching our pattern language for some time. The first step is we give a high-level overview of LPL and software architecture. Then we give a deep dive down into a subset of the pattern language. Then we give a complete overview of structural patterns and how to parallelize them, and that's what I'll do today. Later, we'll have another video where we give a complete overview of computational patterns and how to parallelize them, overview of implementation patterns and their execution targets, and then we'll give a couple detailed case studies. So let's do a quick look at our pattern language. At the top, we have applications going down to structural patterns and computational patterns, a layer of parallel algorithm strategy patterns, and we'll be looking at these two layers today. Later, we'll talk about implementation patterns and execution targets. In terms of patterns in architecting software, once again, we go back and forth between identifying the software structure, identifying the key computations. We do this hierarchically to arrive at the overall software architecture of the application. For example, here we have the software architecture of a real large vocabulary continuous speech recognition, which is again analogous to the design of an entire manufacturing plant. Okay, hold on to your hat. Here's a complete presentation of our structural patterns. Here's the inventory of the 10 structural patterns. In previous videos, we've talked about pipe and filter, iterator, and MAPREDUCE, but let's quickly review those again. So once again, pipe and filter, we have pipes embodying communication. Filters are where the computation occurs. And remember that the filters only see their inputs and outputs and have no global state. Examples of pipe and filter include the compiler that you perhaps use every day. For me, a logic optimizer that I spent a number of years working on. And in a previous video, we talked an image retrieval system. Second pattern is iterator pattern. We begin with an initialization condition. We have a body in which a variety of functions are performed asynchronously. Before exiting the body, we synchronize results of iteration, and we then test an exit condition. If we've met this, we simply continue. If we've not, then we iterate again. Examples of this included our training and classifier and our support vector machine training. Thirdly, MAPREDUCE. Again, to us, it means a map stage where computations are mapped onto independent data sets, and a reduce stage where the results of the map stage are summarized or reduced. Examples of this were included on the actual evaluation of the distance from the frontier for feature vectors and support vector machine training. Now, a new pattern for us is agent and repository. Now, the key to understanding agent and repository is to focus on the repository. The repository is essentially where all the action happens. It's also known as the blackboard. So all the data initially begins in the repository, and the results of the computation when using the agent repository are left in the repository. Blackboard is also an interesting way of thinking about it, in which a series of agents come and write asynchronously on a blackboard, and whatever is left on the blackboard at the end of the computation, that's the result. So these agents do not communicate among themselves, but only communicate through the repository itself. And finally, to orchestrate all the actions of these agents on the shared repository, we have a repository manager. This schedules the access to this shared repository and well as aggregates the results. Some examples of this are, if we look at the global optimization and other optimizations of a compiler, we often see them operating on a single internal representation, some individual internal program representation, and then we might find a number of optimizations such as common subexpression elimination, strength reduction, dead code elimination, constant folding, loop fusion, software pipeline, and so forth, all acting as independent agents, and which can, in such compilers as the SWIFT compiler from Stanford, can be ordered asynchronously. Another structural pattern is the process control. Here, the action is in the process. It's sensed by an individual sensor. That sensor provides input back to a controller. The controller then chooses certain manipulated variables, and then those are chosen to actuate the process. So we have a process, an actuator, sensors, and controller. Now, there are obvious examples of this, such as any kind of process control system, like something as simple as a thermostat, but I like to think of much more sophisticated examples. For example, working for many years on logic optimization, I like to think of an individual logic optimizer in this way, in which the circuit is being sensed for its speed or power, That information gives back to a controller. The controller then gives basically guidance to launch individual optimization transformations on the circuit, and all that is under the guidance of, say, individual timing constraints provided by a user. Another common pattern in web applications is model view controller. In the model view controller, we have a model, which is where essentially the business logic, or in some sense the database, is contained. We have a view, which gives a representation or a view of that data, and controller, which interacts between the model and chooses views. As an example of this, we see a very simple, illustrative example from the book on design patterns, where we have a model, just simple data values. We have views, which can be selected, such as a bar chart or pie chart, and then we have a controller, which can be used to set data in the model, or can be used to arbitrate among the different, or choose different views. Common pattern for structuring systems is layered systems. In a layered system, the individual layers communicate only with paired layers, and this non-adjacent layers in the system cannot communicate directly. Some examples of this are such as an OSI network protocol. So here we see the physical layers, the data link layer, and the network layer, but the physical layer can only interact with the data link layer. The data link layer separates the network layer and the physical layer, and the network layer only interacts with the data link layer. And this allows the details of the implementation of the network layer to be entirely isolated from the details of the physical layer, and then the physical layer can change without having to change the network layer. For more asynchronous event-based systems, we have the event-based system where we have kind of a medium, kind of a C, in which events take place. We have a more centralized event manager, and then we have a wide variety of agents. What's unique about this pattern is that these agents within this medium can be added dynamically. And this is the only structural pattern for which that is the case. So examples of this are the internet itself. The internet is the medium, the signals are IP packets, and the control plane of the router is the event manager. And as we know from the operation of the internet, individual computers can go on or off the internet dynamically. And again, this is unlike any of the other structural patterns that we've considered. The puppeteer pattern arose from the need to manage and control interaction of multiple simulators or computational agents. So the puppeteer itself guides the interaction from among, say, simulation codes to guarantee the correctness of the overall simulation. Problems where the puppeteer pattern is used are often confounded with uses of agent repository, and the key thing to remember here is that there is no central repository, and all the data transfer is between the individual puppets or simulators. So for an example of this, this is a real example that we used with, is the modeling of blood moving in blood vessels. So there was a significant amount of code devoted to the fluid dynamics simulation of blood, and at some point it was thought perhaps we should add this together with another simulator which had been independently developed to simulate the blood vessel. Now these are both very large code bodies, and there was no practical way in which one could share the same underlying data structures. So instead what was developed was a data broker interface. And this data broker interface does two things. Number one, it schedules the relative simulation of the blood vessel or of the blood itself. And we'll notice that if we look in the red and blue here, that the simulation of the blood occurs with a 10 times higher frequency than the simulation of the blood vessel. This reflects the fact that the blood vessel changes relatively slowly compared to the actual blood flow. Then in between the simulation of blood vessels and the simulation of the blood itself, some data needs to be passed, and again, the data broker handles this. Static task graph is the last of our structural patterns. Here, it's very simple. Tasks receive inputs and produce outputs, and all data sharing is through explicit message passing, which is explicitly shown in arrows below. The task configuration, though, is statically defined and may not be changed at runtime. Examples of this is one way of approaching a video game architecture. Here, for example, we have in the input, the artificial intelligence, the physics, other physical effects, and graphics of the game, all expressed as independent, asynchronously interacting tasks. Now, one thing to think about the arbitrary static task graph is it's a bit analogous to the Garland-Shaw call and return architecture in object-oriented programming. And as a developer, when we know that someone has used a static task graph, we haven't got much insight in the application. And for future generations maintain the code, they also don't know much a priori about the code if we see in documentation that they're using an arbitrary static test graph. So we listed this as the last structural pattern, and our general advice is to use this as the last alternative for those reasons.
Hey, I hope you liked this video. If you haven't seen our other videos on the Intel Software YouTube channel, remember to subscribe, and don't forget to leave us a comment. Tell us what other material you'd like to see, and chat with other enthusiasts who watch our shows. We'll see you soon.